So, hello students, I welcome you all on this YouTube channel. So, in the earlier lecture, I have already discussed the armature reaction in DC machines. So, here in that topic, let me give you a quick recap whatever I have discussed in detail. So, armature reaction is nothing but the effect of the armature MMF on the main field flux, right? It is the effect of the armature MMF on the main field flux, right? So, it has some undesirable effect. Number one, there is a net reduction of the main field flux per pole. Due to that, the generated EMF in case of generator reduces. So the terminal voltage falls, it decreases. Second is sparking at the commutator. And third one is distortion of the main field flux wave along the air gap periphery, right? So these are undesirable effects of armature reaction, right? So in this regard, I have discussed that when no load is there, in that case there will be ideally zero current in armature conductors, right? So in that case there will be only one flux in the machine, that is field flux, due to this main field poles north and south, right? So now the resultant flux, it will be in the machine, it will be the field flux. So resultant flux phi r is field flux at no load, right? So MNA will not be shifted in this case, right? MNA, magnetically neutral axis, will not be shifted because MNA is an axis which is basically perpendicular to the resultant field. So here at no load only one flux is there in the machine, that's why the MNA is perpendicular to this resultant flux, that is nothing but field flux only, because there is one flux, that is field flux at no load. Now when you apply load, then this scenario will change completely. So when you apply load, that means the current in armature conductor now starts flowing. They will be having their own MMF, consequently their own flux, that is armature flux, right? So under the influence of this north pole, all the rotor conductors will be having cross, right, for clockwise rotation of generator, right? And for all the armature coils which are under the influence of south, they will be having dot polarity of induced EMF or induced current. So now there are two fluxes in the machine. One is main field flux due to this main field poles north and south, and the second flux is the armature flux, which has now produced due to the application of the load, right? So now there are two fluxes in the machine, and now this armature MMF, it will react with this main field flux phi f, right? So now the main field lines, they will not be straight, they will not remain straight, instead they will be distorted like this, right? They will be distorted and they will be tilted like this, right? So in this context I have explained that these field lines, due to the effect of armature reaction, they will be distorted, they will not remain straight, and due to this due to this resultant flux, which now at loaded condition it will be like this, right? Because now there are two fluxes in the machine, field flux and armature flux, right? So this resultant flux is responsible now for crowding of these main field lines and for distortion of these main field lines at trailing pole tips of the generator, right? So now this results into shifting of magnetically neutral axis, right? And now if the brushes are allowed to remain at their original position, then the sparking will occur definitely and collected EMF will reduce. So to avoid this, the brushes must be shifted to new magnetically neutral axis, right, at load. So I have already explained this, why the magnetically neutral axis is shifting. So all the armature coils which are under the influence of south, they are having cross polarity, and consequently they will produce a flux in clockwise direction like this, right? And hence they will push the main field lines at the trailing pole tips. That means towards the rightmost point of this north, right? That means this is the trailing pole tip, right? TPT stands for trailing pole tips in case of rotation of generator, right? So for generator rotation, for the direction of rotation of generator, in the direction of rotation of generator, this will be the trailing pole tips. So there will be crowding of main field lines due to this resultant main field flux, right? It will push these field lines, these main field lines at the rightmost point of this north pole, and for south it will shift these main field lines at this trailing pole tip. That means towards extreme left side it will push these field lines, right? So this is due to this resultant field flux, and you will get this kind of situation. Have a look at it. So now your resultant field lines, they will be crowded at the trailing pole tips of north and south. For north this is the trailing pole tip, and for south this is the trailing pole tip, right? So this crowding of these field lines, it will occur only at the trailing pole tips in case of direction of rotation of generator, right? So if you allow to remain the brushes at their original position, then sparking will definitely occur, right? So in this context we will now further discuss that why brush shift is required due to change in load, right? So you understand the armature reaction, right? So now we are going to the further illustration. So have a look at it. So here, why brush shift is required due to the change in load. So I have explained that if the load is applied, then the magnetically neutral axis will shift, right? And now there is a requirement to shift the brush. You have to shift the brushes. If you will not shift the brushes, then definitely a sparking will occur, right? So by shifting of these brushes, you can avoid sparking. See how? Have a look at it. So north and south, these are the main field poles, right? This big circle in middle is representing the rotating rotor of the generator, which is rotating in the clockwise direction, right? That is our assumption. So with that assumption, that means for clockwise rotation of generator, we have established the direction of induced EMF or induced currents in these rotor conductors, right? So here have a look at it. For all the armature coils, these small red circles, these are representing the armature conductor or armature coils, right? So now for all the armature conductor which are directly under the influence of north pole, that means for these armature conductor, the polarity of induced current or induced EMF, it will be cross, right? And for all the armature conductor which are under the influence of south, the polarity of induced EMF or induced current will be dot, right? Dot. This I have already discussed, cross and dot. How to calculate the direction of this cross and dot? By Fleming right hand rule. I have already discussed in the earlier lectures, right? Please refer to those lectures. So now my aim is to explain, our aim is to understand that why brush shift is required due to change in load, right? So the answer is to avoid sparking, right? To avoid sparking at the brushes and the commutator surface. So here, see how it can be avoided by brush shift. First we will take the condition when you are not shifting these brushes, right? So here this B1 and B2, they are representing the condition of this brush, right? So B1 is first brush and B2 is the second brush. So this line is representing the magnetically neutral axis at no load condition, right? So this is the original position of MNA, original, or you can say old position of MNA. So when you will not shift the brushes, then sparking will definitely occur. Why? Sparking in which coil? Sparking in that coil which is undergoing commutation, right? Why sparking will occur? Because the coil which is undergoing commutation, that means which is just near to this brush, when it will cross this axis and when it will come under the influence of this north pole, then it will be shorted by this width of this brush. Then this particular coil which is near to this brush, it will be having, definitely it will be having the rotational voltage. It will be definitely having the rotational voltage. E is equal to BLV sin theta, right? So B is the direction of magnetic field lines, L is the length of armature conductor, small v is the peripheral velocity of the armature coils, right? And theta is the angle between B and V, right? So I am saying that for all those coils which are just near this MNA, this coil, they will be having a rotational voltage because theta is not 0 or 180 for all such coils which are near to this old MNA, right? Which is basically MNA at no load, at which you have placed your brushes B1 and B2, right? That means this axis. So see here, let us further illustrate this, why theta is not 0 or 180, due to which you are getting non-zero value of rotational voltage E, right? So have a look at it on this diagram. So I have simply drawn this MNA separately, right? This old MNA I have separately drawn on which the original position of brushes B1 B2 are shown here, B1 and B2, right? So B1 is first brush at its original position without shifting, and B2 is the second brush at its original position without shifting, right? So this shows, this horizontal line is showing the MNA magnetically neutral axis at no load condition, right? So now just analyze. Suppose let us take this coil, the coil which is nearmost to this brush, which is near to this old MNA, right? that is MNE at no load. So here let me take this particular coil which is nearest to this MNA or this nearest to this brush B1, which is the original position of the brush. Then just analyze that this direction of these resultant flux, it is tilted, right? It is not straight because you have applied the load now. Once you apply the load, then armature current will flow in the armature coil and there will be now two fluxes. One is field flux, which were there originally in the machine due to the main field poles north and south, and now the second flux which has just now come due to this application of load, due to the fact that you have applied the load. So armature current IA will now flow and armature flux will be developed, armature flux will be produced, and due to this the armature flux will distort these main field lines, right? I have already explained this effect, why these main field lines are tilted due to the effect of this armature flux, right? It is tilting. This armature flux is pushing these main field lines at the trailing pole tips in case of generator, right? So for north, the crowding of field lines will take place at the rightmost point for north and at the leftmost point for the south pole, right? So at this point you will see the crowding of these main field line will take place, and due to this the main field lines, they are tilted now. They are not vertically straight, they are basically tilted. They are tilted, or you can say they are basically distorted. These main field lines are now distorted. So now see, just take this particular coil which is near to this magnetically neutral axis, or which is nearest to this original position of brush B1. So I am taking this particular coil, right? This coil. So for this coil, just analyze. For this particular coil, just analyze what is the direction of peripheral velocity for the clockwise rotation of generator. It is vertically upward like this. For this particular coil, velocity, peripheral velocity is vertically upward, right? That means this is the velocity. So this red circle is representing the particular armature coil or armature conductor, right? For clockwise rotation of generator at brush B1, this particular coil is having this peripheral velocity. This peripheral velocity, that means clockwise, that means tangentially upward, right? Now tell me, what is the direction of field lines? See, resultant field has now tilted. So this is the direction of resultant field lines. It is tilted. It is not straight like this. It is not straight like this, right? It is basically tilted like this. See this. Due to the effect of this armature flux, it is tilted. So now the direction of main field lines is represented by this green, right? B is showing the magnetic field lines, right, which is tilted due to the effect of this armature reaction. And now you tell me, what is the angle between this small v and this capital V? Small v is the peripheral velocity, and B for Bombay, this is representing the magnetic field lines. So now the angle between these two is this much, right? This is the theta. So due to this theta, this angle is not, this angle theta, this is not 0, neither 0 nor 180, right? So that's why definitely you will get some non-zero value of this rotational voltage for this particular coil, which is nearest to this brush, which is placed at original position, which is not shifted yet, right? So now due to this fact, the rotational voltage in this particular coil is not 0. So that's why when this coil will undergo commutation process, that means when it will be shorted by the width of this brush B1, then definitely it will give sparking, because it is having some voltage, some rotational voltage it is having, right? I have already explained why it is having rotational voltage, because theta is neither 0 nor 180. There is only two possibility for this, for getting 0 rotational voltage. Theta, either it should be 0 or 180, right? That means sin theta must be 0. If the sin theta is 0, that means rotational voltage is 0. So for all the armature coils which are nearest to this brush or nearest to this old position of MNA or nearest to this old position of these brushes, they will be having non-zero value of rotational voltage. So at the time of commutation, when they will be shorted by the brush width, they will definitely give a sparking. Definitely will give a sparking, no doubt in that, right? So when it will cross this axis and come under the influence of north, and when it will be shorted by this brush width, definitely this particular coil will give a sparking because it is having some rotational voltage. E is equal to BLB sin theta, it is not 0, right, for this coil nearest to this brush, right? Now, you understand? Similarly, you can analyze for this particular coil, right, which is nearest to this brush V2. So, for this coil which is nearest to this original position of brush V2, what will be the condition? For this particular coil, when after rotation it will come nearest to this brush V2, then what is the direction of peripheral velocity for this particular coil? It will be tangentially clockwise like this, right? That means this is the direction of peripheral velocity, small v, right, for this particular armature coil which is nearest to this original position of this brush V2, right? Now what is the direction of main field lines? It is tilted, right? It is like this due to the effect of armature reaction. So now this is the direction of main field lines shown by this green arrow, right? So now again there will be some angle between this B and V. So this angle theta is neither 0 nor 180. Definitely again you will get non-zero value of rotational voltage for this particular coil which is nearest to this brush V2. So now when it will go and when it will cross this MNA, old MNA, and when it will go under commutation process, then it will be shorted by this brush width. Again this coil will give sparking because it is having non-zero value of rotational voltage, right? So you understand now? So now sparking will definitely occur. You understand now? So sparking will definitely occur if you will not shift these brushes B1 and B2. Now see, if I will shift these brushes, then this sparking will be avoided, right? See how? To avoid this sparking, just have a look at it. Shift these brushes, right, at the new MNA at load. So this is the new position of MNA. This is the new position of magnetically neutral axis. This is the new position of magnetically neutral axis. When load is applied, then MNA will shift, right? I have already explained this in the earlier lecture. So now you will shift these brushes B1 and B2 at this new position of magnetically neutral axis, right? So when you shift these brushes at the new magnetically neutral axis, then see how sparking can be avoided. So if you analyze this particular coil, right, this particular coil which is just nearby this brush B1, right, this particular coil, when you analyze, then tell me what is the peripheral velocity for this particular coil? Tangentially like this, right, because it is rotating clockwise, so tangentially like this will be the direction of peripheral velocity for this particular coil. So now see, this is the direction of peripheral velocity for this particular coil which is placed nearby to this brush B1, right? So this is brush B1, right? This is your brush B1, right, and this is your brush B2. So when this coil will cross, when this coil during the time of commutation will cross this brush after rotation, then this will be shorted by this brush width, right? And when this coil will be shorted by this brush width, then see what will happen. First analyze, is there any rotational voltage in this particular coil? So peripheral velocity is tangentially like this for this particular coil. That means this is the tangential velocity for this particular coil, which is just nearby this brush B1. And what is the direction of field lines for this particular coil? It is like this in tilted position. These green lines, they are showing the resultant flux field lines, right, due to the main field poles north and south. So the direction of main field lines are like this. So this B is showing the direction of main field lines, resultant flux, right? Direction of the resultant flux is shown by this green arrow. So now tell me, they are just opposite, right? So theta is 180. So that means rotation voltage for this particular coil is 0. E is equal to BLB sin theta, sin 180 is 10. So that's why no rotational voltage is in this coil now, right? Because you have shifted the position of brush. So when this coil after rotation will rotate and come here at this position, and when it will be shorted by this brush weight, then when this coil will come at this position, it will be having no rotational voltage, because theta is 180 for this particular coil, right? So the position of brush has now shifted, and this coil, when after rotation it will shorted by this brush weight, since it is having no rotational voltage, so that's why it will definitely not give any sparking, for sure, no dichotomy in that, right? Similarly, analyze this particular coil, which is nearby this brush bit V2, right? So after rotation, when it will cross this axis, and when it will be shorted by this brush with B2, when this coil will come here, this particular coil will come here, then tell me what will happen. Analyze what is the rotational voltage of this particular coil when it will come at this position of this brush B2. See, peripheral velocity of this particular coil when it will come here, it will be like this, right? Tangentially like this. And what is the direction of field lines? Resultant field flux, it is like this. Resultant flux direction is like this, it is tilted. And what is the direction of peripheral velocity? It is also like this. So see here, B and B, what is the angle between these two? Both are parallel, that means theta 0, right? Theta 0, that means rotation voltage will be 0 sin theta, sin 0 is equal to 0. So no rotation voltage for this coil also, right? So definitely when the commutation process will happen, that means when this coil will be shorted by this brush weight, and when it will come under the influence of the south pole, then during the commutation process, when this coil will be shorted by this brush weight, it will not give sparking. Definitely it will not give sparking. Why? Because it is having no rotational voltage, right? You understand now? So since no rotational voltage is there, so when it will be shorted by this brush weight, it will not give any sparking. Definitely not give any sparking, for sure. No dichotomy in that, right? Why it is happening? Because you have now shifted the position of these brushes, right? So this is the new magnetically neutral axis, right? So always remember, always keep in mind that this brush must always be placed in the latest magnetically neutral axis, right? Suppose if the load further changes and this magnetically neutral axis, if this further shifted and become like this, then you will have to again shift your brush at the new magnetically neutral axis. Otherwise it will again give sparking. Are you able to understand or not? Hope it is clear to all of you, right? So that means you must shift these brushes for the new magnetically neutral axis. So why this magnetically neutral axis is shifted? Because of change in load, right? So when the load changes, magnetically neutral axis will shift, right? I have already explained this. So that means every time when the load changes, can you always shift the brushes? Suppose if the load changes 10 times, then you will have to shift these brush 10 times. That is the meaning, right? and if the load changes 100 times, that means 100 times will you shift this brush. Is it possible? See, this is practically not possible, not at all possible practically, right? So this method of brush shift is only limited to small machines, keep in mind, always keep in mind, right? So for a small machines only this method of brush shift is applicable, right? You understand the practical limitation of brush shifting, right? So by brush shift commutation is improved, definitely. When I say commutation is improved, what is the meaning? The meaning is that no sparking. That means improved commutation, right? But still the terminal voltage is decreasing, right? So generated EMF is reduces because so the terminal voltage is reducing because the generated EMF is reducing, because the field flux is reducing due to the armature reaction. I have already explained this. So to avoid this, right? So to avoid the all practical limitation, brush shift method is not utilized for large machines for sure, right? For large rating machine, for large DC machine, method of brush shift is not at all advisable, right? For large DC machines, right? There we use compensating winding and interpoles to nullify the effect of, to neutralize the effect of armature reaction. We use compensating winding and interpole for large DC machines, right? And when we will use compensating winding and interpoles in large DC machine, then you need not to shift your brushes, right? Because then you will able to counter, you will able to neutralize, you will able to nullify the effect of armature reaction just by using the compensating winding and this interpole technique, right? That we will discuss in the next lecture, right? So how without brush shift and by using compensating winding and interpoles we are able to nullify this problem of sparking, that we will discuss in the next lecture. So my aim was to explain why brush shift is required due to change in load. So you understand now? So brush shift is required due to change in load. Brush shift is required because we want to avoid sparking, right? So sparking can be avoided by brush shift method, by shifting the brushes. But this method, remember, is only limited to small DC machines. Method of brush shifting is only limited to small DC machines and not for large DC machines, right? So hope it is clear to all of you. Thank you very much. Thanks for watching.